Welcome to the Control Systems Upgrade session, everyone. If you'd like to take your seats. Thank you. So nothing lasts forever, and as we've seen this morning, we had some great facility updates to see the status of many of the control projects that have been going on over the last couple of years. This is kind of the complementary session. This is the flip side. This is when control systems get old and they need to be upgraded. And I think that most of the people in the room here actually really like doing this sort of stuff. But this is the hard part, right? Because not only do you have to keep your facility operational, you're also doing a project at the same time. So some of these talks this afternoon in this session are going to go through some of the challenges that you have on both keeping a facility running and doing an upgrade project. So firstly, I'd like to introduce our first speaker, Eric Bjorklund from Los Alamos. Eric received his education at the University of New Mexico and the University of Wisconsin. And he has been a control systems engineer at Los Alamos since, should I actually say, Eric?
You can say. I look it.
Since 1978. So this man is truly a veteran of the control systems area. So thanks, Eric.
Well, thank you for that warm welcome. So, yes, the title of my talk is Replacing the Engine in Your Car While You Are Still Driving It, Part 2. Part 2 because 2 years ago in Melbourne, I gave a talk which is sort of the prequel to this. This then is, of course, the follow-on talk to this. The purpose of these talks is to share with you some lessons we've learned from a very ambitious upgrade program, and also to leave you with some of our observations, recommendations, and anyone here who is attempting a similarly ambitious upgrade may find them useful. To recap, the metaphor of this talk is that negotiating an upgrade schedule is a little bit like driving a car through mountainous terrain with a lot of peaks and valleys. When you start down a valley, you turn the engine off on your car and you replace as much of it as you can. And then you try to put it all back again and make it run before you reach the next uphill section. At the bottom of the valley, there's usually a level place, which is equivalent to the startup, where you just sort of coast while you try to figure out what your modifications may have done to the machine. So, last time, the observations we made were, 1, you can't replace the whole system at once. 2, because you can't, some compatibility must be maintained between the old and new systems. And 3, you will be surprised. The recommendations were 1, always have a way to fall back, and 2, have sympathy for your operations staff. Now, in this talk, we will be making some amplifications on those observations and actually adding one more recommendation for your pleasure. So this is the scope of the project. We've divided it up into 9 sub-projects with the added caveat that we have to continue to be delivering Beam to our customers. Last time, I talked mainly about the timing system, but timing is only one part of your engine. So this time, I want to focus on 3 other subsystems: the industrial I/O system, the Beam synchronous data acquisition system, and the Fast Protect reporting system. Now, the reason for choosing these 3 items is they actually all belong to one mega system called Remote Information and Control Equipment, also known as RICE. So here's how RICE works. First of all, it's been there longer than I have. It was designed and built in the late 60s and originally provided all of the control and data acquisition for the accelerator. A typical RICE station provides binary and analog control with 12-bit resolution and has 3 primary functions. There is a Beam synchronous data acquisition function, there is a Fast Protect monitoring function, And then there's just your standard industrial I/O function. You can have up to 128 RICE stations which interface through serial links to one RICE interface unit, or RIU. One RIU read operation then will return up to 128 data words, one from each station, and they will all have been read at more or less the same time, plus or minus a few random cable delays. So this is how the RICE system handles beam synchronous and fast machine protection data acquisition. The RIU then interfaces to a microvax, another old piece of equipment, and the microvax then serves that data to the network, and it can be had by all of like the EPICS nodes that we want. The system worked well for a while, but as time progressed, it also became one of our biggest bottlenecks, especially during tune-up session in which we were using a lot of beam synchronous information. So this leads us to, again, to recap our first observation. You can't replace the whole system at once. So we divided that into 3 subtasks. Industrial I/O, where we would use National Instruments compact Rio crates running EPICS. Fast protect reporting, which was going to be replaced by compact PCI crates with timing modules and binary input cards. And the beam synchronous I/O, which is going to be replaced with VPX crates, timing modules, and waveform inputs. But none of these sub-processes could be completed at once either. So that leads us to observation number 2, which is some compatibility needs to be maintained between the old and the new systems. Until we can get each entire subsystem converted, the control system will have to deal with data from both sources. Now, this is not a problem for industrial I/O because the data of both sources are pretty much independent of each other. But it is a problem for beam synchronous and fast protect readbacks because they must return data that was simultaneously sampled by both systems. Now, like many other facilities, we use a correlator program to combine the data from both the old and the new systems. The data is correlated by timestamp, and in order to make life easier for the correlator, we only timestamp the beam pulse. Everything that happens in that pulse has the same timestamp, and therefore correlation can be achieved by direct match or exact match. So the way the timestamp gets to the data on the new system, the timestamp comes from the timing event link, and is basically just timestamped on the basic record, IOC EPICS records. However, Micro Research Finland has not yet provided us with an event receiver that interfaces to a microvax Q bus. So we can't use the event system to timestamp the RICE data. So here's what we do. First of all, we aren't actually using all 128 of those stations that the system is capable of. So you find 3 that aren't being used. You put in a IOC with an event link and 3 12-bit digital outputs. We connect the digital outputs to that bus, and now the RICE data set itself contains within 3 words enough of that timestamp to deduce an exact match. So now we come to observation number 3. You will be surprised. But sometimes the surprise is pleasant. So here's our pleasant surprise. So in 2015, we replaced the individual I/O function in the individual industrial I/O functions in 4 RICE stations. In 2016, we replaced the industrial I/O function in 7 RICE stations. A bit of an improvement, but at this rate, we were kind of on track to finish somewhere between 2013 and 2025. So, to our great surprise, in 2017, we replaced 33 RICE stations, approximately half of all the RICE stations that we have operational. So how did we do that? Well, there are 3 things that happened. First, we actually had more people working on the job. That doesn't necessarily guarantee more efficiency, but in this case it did. The 33 that we replaced were all along the LINAC, and they all were pretty much had the same kind of configuration. So we got a lot from some redundancy there. But the thing that really did the most for this particular miracle was the change of tactics, which leads us to my new recommendation. Most do as much as you can before the maintenance period starts. Now, most of the productivity gain in 2017 was due to planning. The project lead inventoried all of the existing wires during the operational period, cross-checked them with the device tables to make sure that they were unused, removed all of the unused wires, removed all of the trunk cables that only had unused wires, labeled all the wires so you know where they went, installed the terminal strips, and made sure that the compact reels that were going to replace them had already been built. So the result was that during most of the maintenance period, most of the work just consisted of moving wires from one place to another. So here's the current state of our system. We are over halfway finished with the replacement of the industrial I/O. We are over half of the way finished with the replacement of the Fast Protect readback. Our beam synchronous data is just getting started, but we are waiting eagerly for that. And over this last shutdown, we replaced over 4,500 channels, which is a very significant load reduction on the RICE system. So I can now stand here and report to you that that pesky bottleneck that has been bothering us for years and years and years got worse. Sometimes the surprise will not be pleasant. So what happened? Well, the only honest answer I can give you is, we don't know yet. We have the light bulb, but it hasn't gone off yet. We have our theories, one of the best of which is that beamline physicists, giddy at the prospect of having a more responsive RICE, have been piling more and more requests for beam synchronous data onto the system and loading it down even more than what we unloaded it. But we don't really have any data yet to prove that. We're still investigating it. So the best answer I can give you right now is to be continued. So in conclusion, I would like to thank Christy Carr, who is the cartoonist for this presentation, and to thank all of you for your attention. And see, Nick, I did do 59 slides in under 12 minutes.
Yes, Eric has just created the ICALEPCS world record for the most number of slides in 11 minutes. So I open the floor to questions.
So microphone to... There we go.
I'm curious to know whether you have any spare equipment which is able to be to replace the old hardware which you have in your system.
Any spare equipment?
Yes. If you have any, if one of these elements fails, how do you replace it now if they are obsolete?
So what we do have spare cards that we maintain, and we have been maintaining them for over 40 years now. But yeah, so when a card goes bad, we pull it out. Does that answer the question? So yes, we do have spares. So we can continue to run.
So given the experience you've got in replacing the engine on this car while you're driving it, have you designed the new engine to be more easily replaced when you come to repeat the exercise in 2042?
Well, I strongly suspect I'm not going to have to address that personally, but my opinion on that is basically modularity. And keep that small. God knows what we're going to be looking with, perhaps quantum computing by 2014. So it's, if you were starting it right now, though, I would definitely look at the sort of coming up technologies, and go and see what the new systems are doing. See what's new. Come to an ICALEPCS and find out what the latest thing is, and then say, hey, I got to do that.
We've got time for one more question. If there's not from the floor, I'll take one. Eric, What caused the management to decide to pull the trigger on doing that now rather than, or 2 years ago or 4 years ago when you started, rather than sometime previous?
Okay. So actually that question is answered in the first presentation where I put up the schedule. We actually started this 6 years ago. We are now sort of in the middle, at the last third of that replacement system. So for example, we have already replaced the timing system. We've already replaced the network infrastructure. And those things have sort of all gone on. Well, actually the timing system is still in process of being replaced, but we have its thing in function. So yeah, we've actually been working on this now. It's a 9-year project. We started this 6 years ago, and we're hoping to end it in 2019.
Good. So would everybody like to give Eric a round of applause? Thanks.